Welcome to our comprehensive guide on calculus, where we'll break down the essentials of both differential and integral calculus. Whether you're a student preparing for exams or someone looking to refresh your mathematical skill, this video will walk you through the core concept, practical example, and real-world application. We'll start by understanding what calculus is, why it's important, and how it forms the foundation for advanced studies in mathematics, engineering, and science. Function is a rule that assigns each element from one set, called the domain, to a unique element in another set, called the range. In calculus, functions are the building blocks for understanding change and accumulation. There are explicit functions, where y is directly expressed in terms of x, and implicit functions, where the relationship between x and y is not straightforward. Recognizing the type of function is crucial for applying calculus techniques effectively. Let's look at some. Functions come in various forms: algebraic, trigonometric, exponential, logarithmic, and more. Algebraic functions include polynomials like y barabar x2 plus x plus a. Trigonometric functions involve sine, cosine, and tangent. Exponential functions have variables in the exponent, such as y barabar ex, while logarithmic functions are the inverse of exponential. Understanding these types helps us choose the right calculus tools for solving problems. Functions can also be classified as even, odd, or periodic. An even function satisfies fx barabar fx, like x2 or cos x. An odd function satisfies fx barabar fx, such as x10 or sin x. Periodic functions repeat their values in regular intervals, with sine and cosine being classic examples. Recognizing these properties is helpful when analyzing graphs and solving calculus problems. Let's practice evaluating functions. If fx barabar x2 plus 1, then f2 is 2 plus 1, which equals 5. For fx barabar 2x2 4x plus 6, f2 is 2 4 2 plus 6, resulting in 22. These examples show how to substitute values in the function, a skill that's essential for calculus operations like differentiation and integration. Limits are a fundamental concept in calculus. They describe the value that a function approaches as the input gets closer to a certain point. Limits help us define derivatives and integrals. For example, the limit of fx as x approaches a is written as lim xa fx. Mastering limits is the first step toward understanding how calculus measures change. Limits follow several important properties. For instance, the limit of a sum is the sum of the limits, and the limit of a product is the product of the limits. These rules allow us to break down complex expressions into simpler parts. Understanding these properties is crucial for evaluating limits efficiently and accurately. There are several methods to evaluate limits: direct substitution, factorization, and rationalization. Direct substitution works when plugging in the value doesn't result in an indeterminate form. Factorization and rationalization help resolve cases like *0/0 or *∞/∞. Knowing when and how to use each method is key to solving limit problems. Some limits have standard results, such as lim x0, sin x/x barabar 1 or lim x0, ax1/x barabar ln a. Memorizing these standard limits saves time and helps solve more complex problems. These formulas are frequently used in differentiation and integration. Let's work through some solved examples. For instance, lim x1 plus x2 plus x10 equals 0 after substitution. In another case, lim x2 x10 art/x2 initially gives 0/0, but after factorization, the limit is 12. Practicing these examples helps reinforce the techniques for evaluating limits. When x approaches infinity, limits often involve simplifying expressions by dividing by the highest power of x. For example, lim x plus 1, x plus 2/x plus 10, x plus 4 simplifies to 1. Understanding how to handle infinity in limits is essential for analyzing the behavior of functions at extreme value. Trigonometric limits often use standard results, such as lim x0, sin x/x barabar 1. For example, lim x0, sin x/x uses this property and simplifies to /6. Mastering these techniques is vital for calculus involving trigonometric functions. Differentiation is the process of finding the rate at which a function changes. It's the core idea behind derivatives, which measure how a function's output varies with its input. Differentiation is used to find slopes, rates of change, and optimize functions in real-world scenarios. Derivative of a function y barabar fx is defined as the limit of the average rate of change as the interval approaches 0. It's denoted as di/dx or fx. This concept allows us to analyze how functions behave at every point, not just between 2 points. Derivatives have real-world meaning. For example, if distance is a function of time, the derivative gives velocity. If velocity is differentiated, we get acceleration. This physical interpretation makes derivatives a powerful tool in physics, engineering, and economics. Differentiation follows several properties. The derivative of a constant is 0, The derivative of a sum is the sum of derivatives, and there are product and quotient rules for differentiating products and quotients of functions. These rules simplify the process of finding derivatives for complex expressions. There are standard formulas for derivatives, such as d/dx xn बराबर nx n1, d/dx sin x बराबर cos x and d/dx ex बराबर ex. Knowing these by heart allows you to quickly differentiate common functions and build up to more complex problems. When differentiating the sum, product, or quotient of functions, use the respective rules: the sum rule, product rule, and quotient rule. For example, the derivative of y बराबर x cos x uses the product rule. Practicing these rules helps in handling more advanced calculus problems. The chain rule is used when differentiating composite functions. If y बराबर f gx, then d/dx बराबर f gx तारांकन gx. This rule is essential for handling functions within functions, such as y बराबर sin 2x plus 1 or y बराबर tan cos x. Logarithmic differentiation is useful for functions where both the base and the exponent involve variables, such as y बराबर xx. By taking the logarithm of both sides, we can simplify the differentiation process and solve otherwise challenging problems. Sometimes, both x and y are given in terms of a third variable, like t or theta. In such cases, we use parametric differentiation, d/dx बराबर d/dt/dx/dt. This technique is especially useful in physics and engineering for analyzing motion and curves. First derivative gives the rate of change, but we can differentiate again to get the second derivative, which measures the rate of change of the rate of change. Higher order derivatives are important in physics for acceleration, curvature, and more. Derivatives are used to measure rates of change in real life. For example, if y बराबर x3 plus 5, x2 6x plus 7, and x increases at 10 units per minute, we can find how fast the slope changes at a specific x. This is crucial in physics, engineering, and economics. Derivatives help us find slopes of curves, rates of change of area, volume, and more. For example, the rate of change of the area of a circle with respect to its radius is dA/doctor बराबर 2 pi. These applications show how calculus is used in geometry and physics. Maxima and minima are the highest and lowest points of a function. Calculus provides a systematic way to find these points using derivatives. This is essential for optimization problems in engineering, economics, and science. Find maxima or minima, set the first derivative equal to 0 and solve for x. Then, use the second derivative to determine if it's a maximum, second derivative negative, or minimum, second derivative positive. This method is widely used in optimization. Let's see an example. For f(x) बराबर x3 12 x2 plus 5, set the derivative to 0 and solve for x. Then, check the second derivative to classify the points. Practicing these steps helps you master optimization problems in calculus. Calculus is used to solve optimization problems in geometry, such as finding the rectangle with the largest area for a given perimeter or the minimum sum of two numbers with a fixed product. These problems illustrate the power of calculus in practical design. Integration is the reverse process of differentiation. It's used to find the total accumulation of quantities, such as area under a curve or total distance traveled. Integration is a key tool for solving problems in physics, engineering, and beyond. There are standard formulas for integration, such as xn dx बराबर xn plus 1 / n plus 1 plus c and 1 / x dx बराबर ln x plus c. Knowing these basic integrals allows you to solve a wide range of problems quickly and accurately. Let's practice integrating some functions. For example, x3 dx बराबर x4/4 plus c and 2x2 plus 3x plus 5 dx बराबर 2/3x3 plus 3/2 x2 plus 5 x plus c. Practicing these examples builds confidence and skill in solving integration problems. When the integrand is complex, substitution can simplify the process. For example, to integrate 2x plus 3 dx, let u बराबर 2x plus 3, then do बराबर 2 dx. This method is powerful for handling a wide variety of integrals. Integration by parts is used when the integrand is a product of two functions. The formula is u dv बराबर u dv, 2 dv. Choosing which function to assign as u and dv is guided by the Illet rule: inverse, logarithmic, algebraic, trigonometric, exponential. Integrating trigonometric functions uses standard formulas such as sin x dx बराबर cos x plus c and cos x dx बराबर sin x plus c. These are essential for solving problems involving waves, oscillation, and circular motion. Definite integral calculates the accumulation of a quantity over a specific interval. For example, x to dx gives the area under the curve from x barabar 1 to x barabar 2. Definite integrals have real-world applications in finding areas, volumes, and total quantity. Let's solve a definite integral p/4 sin x dx. The result is cos x from 0 to p/4, which equals 1/square 2. Practicing these examples helps you understand how to apply definite integrals to real problems. Reduction formulae simplify the evaluation of integrals involving powers of sine and cosine, especially over intervals like 0 to p/2. These formulas are essential for advanced integration problems and save time on complex calculations. Integration is used to find areas under curves, volumes of solids, displacement, work done, and average values. For example, the area under y barabar 1 plus 2x from x barabar 0 to x barabar 2 is found by integrating and evaluating the result at the endpoints. When exact integration is difficult, numerical methods like the trapezoidal rule provide approximate solutions. This rule estimates the area under a curve by dividing it into trapezoids and summing their areas. It's widely used in engineering and data analysis. Simpson's rule is another numerical method that provides more accurate results by approximating the curve with parabolic segments. It's especially effective when the number of intervals is even and the function is smooth. Differential equation involves an unknown function and its derivatives. These equations model real-world phenomena in engineering, physics, biology, and economics. Understanding how to classify and solve differential equations is a key skill in applied mathematics. The order of a differential equation is the highest derivative present, while the degree is the power of the highest derivative after removing radicals and fractions. Knowing the order and degree helps determine the appropriate solution method. First-order differential equations can often be solved by separating variables and integrating both sides. For example, dx barabar sin x leads to y barabar cos x plus c. This method is fundamental for solving many real-world problems. Differential equations are used to model population growth, radioactive decay, heat transfer, and more. By solving these equations, we can predict future behavior and optimize systems in science and engineering. Statistics is the science of collecting, analyzing, and interpreting data. In calculus, statistics helps us understand data distribution, central tendencies, and variability. Key measures include mean, median, mode, and standard deviation.